In this video, we're going to take a look at two properties of sets of vectors now. One is what it means for a set to be orthogonal, and the other, which is related, what does it mean for a set to be orthonormal? So let's set the framework here. So we have V is an inner product space, right? And we know what that means, right? Inner product space. And then let's say, so VI, so these vectors are elements in V. And let's say S is just a set of these, right? So V1, V2, dot, 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 Vn. All right. Now, we know what it means for a pair of distinct vectors to be orthogonal. Like if I give you U and V, and I say, hey, here's an inner product, tell me if these two vectors are orthogonal. Well, you would compute their inner product, and if their inner product is 0, boom, the conclusion is that they're orthogonal. Well, what would it mean for an entire set, right? Multiple vectors, multiple greater than 2 to be orthogonal, it means that every distinct pair of vectors, or I should say pair of distinct vectors, are orthogonal. So let's define that, write it down, and take a look at it. So S is orthogonal if and only if. I mean, every definition is if and only if, right? If this is true, the inner product of VI and Vj, if that inner product is always 0 as long as I is not equal to j. So in other words, you're not going to check the inner product of a vector with itself, but just with a vector and all other vectors in that set. And if all the inner products come out to be 0, then it means that our set is orthogonal, right? And again, you might be saying, what on earth is that useful for? Well, it turns out if you think that a basis of a vector space is important, and you should, then you'll see how orthogonality relates to having a basis, all right? Okay, so that's what it means for the set to be orthogonal. So if in addition to this property, if all the vectors in the set are unit vectors, right, and we know what that means, then the set becomes orthonormal. So it's like you just keep adding more properties, right? So I'll just say this. So if, let's start with an if here. So if we already know that we have a orthogonal set, so if S is orthogonal. So we've already checked this and we verified it, right? And now remember, the requirement for us to have a unit vector is when the inner product comes out to be 1, right? Which would then imply that it has length 1, right? So if the inner product of VI and itself, now this is where you're checking each vector and itself. So if that inner product comes out to be 1, which is another way of saying, in fact, let me write this a couple different ways. You could say, remember that when you take the inner product of a vector with itself, you're getting the norm of that vector squared. So you could say that the square of the norm is 1, or because 1, you can easily take its square root, you could say that the magnitude or the norm by itself is equal to 1. So all of these are equivalent. So if you start with an orthogonal set and then each of the elements in that set are unit vectors, so here's the conclusion. So then S is orthonormal. So the ortho is the orthogonal part. The normal has to do meaning that the vectors have been normalized, right? And because of some of the algebraic properties that we've used for inner products, if you have an orthogonal set, it's actually pretty easy to convert it to an orthonormal set. So it's really, the focus is finding these special sets, right? So let's just, maybe just do a couple examples so you can see what's going on. Nothing earth-shattering. So let's take a look at example 1. And you've actually seen, you've seen many examples of orthonormal sets from our work with bases, right? So let's take a look at, let's say we're in R2, right? Remember the standard basis for R2, so that's our E1, E2. So in fact, yeah, let me just call that S. In fact, if you wanted to write it out explicitly, let's write it in the n-tuple form. So remember, E1 is our 1, 0, and E2 is our 0, 1. All right, it should be pretty easy to verify this, right? So there are only 2 vectors to check. So this would be like my V1, this would be my V2. And again, anytime you're talking about a Euclidean vector space, unless we say, okay, use some other weird inner product, you're going to go ahead and use the standard Euclidean inner product, which is our dot product. So if I just call this one V1 and then this one V2, so let's do our check. So first we're going to check for orthogonality. So that's just V1 dot with V2. And it will be 1 times 0 plus 0 times 1, which is 0. So yes. So S is orthogonal. I don't have multiple pairs to check. There's only one pair here, so that's it. Then now, let's check the magnitude of each of these. Again, I mean, we've referred to these as unit vectors, so we know how the story is going to end. But the norm of V1, yeah, that's just the square root of 1 squared plus 0 squared, again using our Euclidean inner product, and then that's 1, and then same thing, the magnitude of V2, that's 0 squared plus 1 squared, which is 1, so check, check. So this means S is orthonormal, right? And I also want to point out that, the fact that, and remember, this is what we refer to as the standard basis for R2, or in general, we have a standard basis for Rn. And when we use the standard basis, which now we've realized has this property of orthonormality, is that it makes it pretty easy to do things like compute coordinates relative to a basis. And the question is, is that always the case? It turns out yes, right? And we'll see that in a future video. Here we're just introducing the ideas. Let's take a look at something that let's take a look at example 2, and I want to look at something where the vector space is not Euclidean, but let's say it is. Let's use C. So let's look. We haven't worked a lot with the space of continuous functions. Here I'm just going to go on the interval 0 to 2 pi. And then let's say here's our S. So it is 1. It is, let's just take sine of x, and then let's take cosine of x. Right? So that's my set of vectors, and we should be able to agree that these functions are all continuous on the interval 0 to 2 pi. And so now, since this is a non-standard thing, I have to tell you what inner product to use, and we're going to use this as our inner product. So to find the inner product of any 2 vectors, we're going to take the integral from 0 to 2 pi of the product of these 2. So f of x times g of x dx. All right? So let's go through and check for orthogonality. Now, because these are, because we have 3 functions, and we need to check 3 integrals. In other words, if I think of this as f and g and h, sorry, make that an h, we have to do f and g, f and h, and then g and h. So that means we have 3 integrals to compute. So I guess using the labels that I have here, let's just go ahead and check the first pair. So let's check the inner product of f times g. So that's the integral from 0 to 2 pi, and then we multiply that, we get the sine of x, so that's dx. Antiderivative of sine is negative cosine, and then we go from 0 to 2 pi, and then let's do the negative of, so the cosine of 2 pi, well, that's 1, minus the cosine of 0, that is also 1, and there you go. So we end up getting 0. So that means relative to this inner product, the function 1 and sine of x, they're orthogonal. Well, let's see what happens if we do 1 and cosine x. So let's do f and h. So let's take the inner product of f and h, see what that is. So we go from 0 to 2 pi. This time we're going to be integrating 1 times the cosine of x, which is just antiderivative of cosine is sine. Then we're going to evaluate that from 0 to 2 pi. And now, so the sine of 2 pi is 0. In fact, I don't have to write that. And then the sine of 0 is 0. That's also 0. So this pair is orthogonal. And then let's take a look at now g times h. So let's do, or g and h. We check the last pair. So again, 0 to 2 pi, and now we have a little bit of work to do because we got sine x times the cosine of x. And there are lots of ways you can approach this. There's you can do a standard u sub. You can let your u, for instance, be the sine function, and then your du will end up being exactly cosine of x dx. Or if you're pretty clever, you might recognize this as a trig identity. In fact, it's related to the double angle for sine. So sine x times cosine x. In fact, let me show you the little trick here, just an intermediate step. If I multiply this integrand by a half and 2, so let me take out a 1/2 and then double it. So I'm basically multiplying by 1, and then it looks like that. Right, now this integrand is the same as the sine of 2x. Right, so we can sort of rewrite the integrand, but we need to do that 1/2 thing. And we got the integral from 0 to 2 pi, and then this gives me the sine of 2x dx. And then when I integrate, I will again end up getting, so we have that 1/2 there, but then I end up getting a negative 1/2. Again, reversing our chain rule, and we got the cosine of 2x, and then that goes from 0 to 2 pi. But it's, we look at what's going to happen. So this is negative 1/4. Cosine of 4 pi is still 1. Cosine of 0 is 1. And there we go. So it's 0. Yep. So we end up getting that S is an orthogonal set, right? And I just wanted to verify the orthogonality of this set, and I will leave it for you to see if this is orthonormal. But if you check just the f function, think about what you would do to check the f function. You would take the inner product of the f function with itself, which is just 1 times 1, and then you're going to integrate that from 0 to 2 pi, and I don't think that's going to give you 1, right? In other words, we would expect that inner product to come out to be 1 if the f function is going to be a unit vector. So when you verify it, and I do encourage you to do it on your own, you'll verify that, yeah, these are not unit vectors relative to this inner product, all right? So again, I mentioned earlier that there is a relationship between orthogonal sets and bases of these vector spaces. And so I want to end with kind of a theoretical result, but an important result, in that if we have a set What I will do is I will state the, in fact, let me end this right here because that's the end of my example. So let me start with let's say that S is an orthogonal set. So let S, and again, I'll just keep it as my V1, V2, dot, 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 Vn. So let this set be orthogonal. I don't know what vector space, I don't know what inner product, or I'm not specifying anything like that. Let's just say we have an orthogonal set. And what I want to do is establish a relationship between orthogonal sets and the idea of linear independence. Now remember, the definition of linear independence is that this equation, so consider our vector equation, that famous homogeneous equation. So C1 V1 plus C2 V2 plus dot 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 Cn Vn is equal to this. All right. So remember if we want to maybe conclude that once we know that the set is orthogonal, then it has to be linearly independent, we have to show, so here's our goal, we have to show that each of these coefficients have to be 0. In other words, this vector equation, this homogeneous equation, has to have only the trivial solution, and then we can conclude that our set is linearly independent. So how would we do that? Well, what we're going to do is take the inner product of both sides of this vector equation, right? So we're going to do a big inner product with each of the vectors in the set itself, but we're going to do it in a general way. So in other words, I would take V1 and do the inner product of both sides. Then I would take V2 and do the inner product of both sides, and so forth. But let's just do it with VI to keep it general, right? So let's do VI, comma, and then I have to write down this whole thing here, C1, V1, plus C2, V2, plus dot, 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 Cn, Vn, and we're going to do that inner product. And then if I do it on the left, I have to do it on the right. So then it's going to be the inner product of Vi. Yeah, that's one of our vectors. And then, of course, the 0 vector. So here's what's going to happen. When you do the inner product with the 0 vector, you're going to get a 0 here. So you're going to get a big fat 0 here. Now, we have to use some properties of the inner product. Remember the ones like the distributive and the scalar. So when you apply all those properties together, and I'll write down the expression. So when I do Vi with just this term, I'll be able to factor out the C1, and then I will have the inner product of Vi with V1, like that. And then I will add to that, this is the distributive property, so when I get to the second term here in our linear combo, take out the C2, and then you'll have Vi again with the inner product with V2, and then dot, 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 plus last term here, take out the Cn, and then you'll have the inner product of your Vi, whatever that is, with Vn. All right, so what does this mean? Well, let's use the fact now that S is orthogonal. And remember what it means for the set to be orthogonal is that every inner product with a vector except itself is going to be 0. So for all of these, right? So as long as, here's what I would say. So your Ci, and then V, oh, sorry, yeah, so Ci, this needs to be an angled bracket. So this term, Vi, and then Vj, that term has to be equal to 0 except when I is equal to j. So for I equal j, right? I'm sorry, yeah, when I is not equal to j, then the inner product, and that's because the set is orthogonal. So all it means is there's going to be one term left on this side that's not 0. Well, what is it going to be? It's going to be your ci vi with itself, right? That one can't be 0. Oh, I'm sorry. No, I'm sorry. Yeah. So yeah. So that's the term that we have left. Then now I'm gonna bring down the equal sign. I'm sorry, equal 0 here, right? Now remember what we had said. When you take the inner product of a vector with itself, you're going to get a non-negative quantity. So this term right here is not equal to 0, right? So in fact, let's write it like this. So ci, and we know another way to write this would be your vi, norm of vi squared. That has to be equal to 0. And since we have non-zero vectors, right, in our orthogonal set, then the norm of vi squared, that can't be 0. So divide both sides by this non-zero quantity. So this implies that ci has to be equal to 0. All right. So look at the implication, right? So if we start with an orthogonal set, then the solution to our vector equation here has to be the trivial solution, because this is saying that all the constants, the ci's, all of these have to be equal to 0. So this implies that S is linearly independent, which is we know how important linear independence is, which now implies that orthogonality has to be equally important, since orthogonality implies linear independence. All right. So yeah, so I'll just end on that little important note. But yet we're going to take this idea and keep building. So if you're in the mood for some mathematical construction, see me in the next video.